Mike Groh. I work for an independent water treatment consulting firm and lab. We don't sell chemicals. We don't sell equipment. We basically help everybody make sure that the water treatment companies are doing what they should be doing. And then they have a direct impact on water conservation and also treating the buildings and stuff. I do have the advantage, and I get to see a lot of water treatment companies. I get to see a lot of applications. I get to see a lot of cooling towers. And I'm going to share some of those experiences with you. So what do we see out there? Well, we don't see a lot of good things in many cases. White rust is some of the things that have been around haunting us for a couple years. For anybody that has, how many people have galvanized towers here? How many people see white rust here? Okay. Basically, white rust is zinc carbonate, okay? Basically, these towers are coated with galvanized, okay? And the galvanized is basically a sacrificial metal. That's its design. Its design is to protect the under metal surfaces of the cooling towers, and so they coat it with zinc, basically. Well, zinc does not like high alkaline water, okay? And so it forms zinc carbonate, which are white bubbles, rust pockets, basically on the surface in there. And so what you're doing, you're basically leaching out zinc and forming zinc carbonate. And you can take these things like little dust things and remove them. But the problem is you're removing the barrier that's protecting the steel cooling tower itself. We're seeing a lot of our clients moving away from galvanized towers. Unfortunately, they're still very, very inexpensive, so we still see them coming out. So there might be changes in the water treatment program that you need to do to help protect that, especially in the first 90 days. These towers need to go through a process of passivation and pH control to passivate that zinc barrier before you start the water treatment program. If you don't do that, you're going to see pretty rapid deterioration of these towers, so they won't last very long. Obviously, with all the technology we have, we're seeing still way too much scale formation in cooling towers. Here's an example of a plant I visited a couple weeks ago. It's a high hardness area of the country, and they just didn't take a look at their water treatment the way they should. They basically scaled up their entire fill right there. Once you scale up a system, it can be cleaned. It's painful. It's very painful, because the only way to really remove scale is by dropping the pH, which puts the tower system somewhat at risk from a corrosion standpoint. So there are ways to do it, but the best way is don't let it happen in the first place. Obviously, the one thing that cooling towers do have is that they are perfect breeding grounds for biological activity, as well as algae. Algae needs sunlight on top of everything else, but when you think about it, a cooling tower has the heat. That's what you're trying to remove, so it's a warm environment. It's got water. Okay, if you ever sat next to a cooling tower or stood next to one, you get sucked in, you know, because it's basically an air washer. So it's sucking in nutrients, materials, suspended solids. So you're feeding it, you got warmth, and you got water. So it's a perfect breeding ground for biological activity. One of the things that you want to do is that if you look inside the tubes, if you have a condenser tubes, most of the tubes now are what they call enhanced tubes. They're enhanced not only on the outside on the freon, but they're also enhanced on the inside. And it's basically a rifle barrel that goes through there. I don't know if you guys can see that very well. Can you see that very well? Did it come out in place? Basically, it's a rifle bearing that goes through the tubes, and the purpose is, again, is to increase the surface area of the tube. So by rifling it, you've got the valleys and grooves and everything else, so you actually increase the surface area of the tube, allowing better heat transfer surface. One of the problems is a lot of people don't look. They can look when you do your tube inspections. Okay, you can only see about the first 3, 4, 5 inches, but you really can't see down the tube. Okay, so when we have borescoping, or we send an optic eye down there, we can actually see the inside of the tube and what's happening in the different hot zones of the condensers. In this particular case here, we see the black material is a fouling material from biological and dirt and debris. We're seeing a little bit of the copper corrosion over here. The green is actually copper oxide, and we're starting to see a little bit of scale formation on top of the tubes. If you were to run an eddy current, and which they did on this plant, they ran an eddy current study down there, which is basically determining the thickness of the tubes. The eddy current showed that this tube was fine. There was no problems, no defects in this tube. But you can see that this tube is heading into some disasters in a couple years, because the water treatment program is not really effective. You're either going to scale it up, you have some copper corrosion, which is eventually going to go through the copper itself, which the eddy currents will pick up. The question is, will you do the next eddy current before you have a tube failure? And you're seeing biological activity, which we'll talk about, biologically influenced corrosion. So it's always a good idea to try to do both borescoping as well as eddy currents in between times to find out what's going on. Nice thing about borescopes is that you can see what's going to happen to you in a couple years. Eddy currents obviously tells you whether or not you're actually seeing metal loss in the tubes. These tubes are 25 1,000ths of an inch thick. I don't know if you can visualize that. 25 1,000ths of an inch thick. You don't have a lot of room to work with. You know, they normally condemn a tube when it's 50% loss. That's 12 and a half thousandths of an inch. So the tolerance levels are very, very small, and they do that on purpose because the heat transfer efficiency is so great on that. Nice thing about the borescopes is we can actually take perpendicular angular shots of the tubes themselves. Here's an example of a tube that's got biological fouling. You can see the enhancements right here, and you can see the biological, it's like a gelatinous material that's in between these things. That actually acts as an insulator to the tubes as well, and also causes biologically influenced corrosion. In other words, bacteria basically, in its metabolic rate, secretes acids. So right there on the pipe surface there, you're going to secrete acids, and that could cause damaging to the tubes. Here's an example of an enhancement where it was completely filled with biological activity. Okay, so all the enhancements were filled up, and actually this machine is losing efficiency and could cause problems. This client right here, finally, it cost this client about $100,000. Here we actually found a hole in the tube itself. It actually pitted through the tube right there, allowing water to get into the Freon side, and water and Freon don't mix very well. Very aggressive material. It causes rapid corrosion inside the chiller. So this cost about $100,000 to replace this chiller and retrofit this chiller because of the pitting occurred on the tube surface itself. I know this picture's fuzzy, but here's an example of you can see actually the enhancements right there. You can see the copper corrosion. In this case, you can also see tube defects. This is where the enhancements have actually split off from the tube itself, so it's actually a tube defect from the manufacturer. We certainly recommend eddy currents and borescoping be done on all new chillers. It takes away the finger pointing a year later on whether or not there was actually tube defects or not tube defects. It's not uncommon to see tube defects, guys. We just did a property out in Hawaii, brand new chiller, 1,200-ton chiller, 2 of them. We eddy current borescope, we had 50 defective tubes. It's not a good sign. That's ugly out there, but it's not uncommon to see these things. It's nice to get those things documented and get baselines done right away. Here's an example of a closed loop system. Closed loop systems are not immune to corrosion of biological fouling if you don't treat them. Basically, you have, most of them are steel pipes, so they close them all up. Here's an example where we saw a lot of corrosion in the pipe surface itself. The piping itself is iron, it's FeO. Okay, we take ferric oxide from the ground, we actually mold pipe. Pipe does not want to be in a natural state of iron. It wants to be rust. That's where its natural state is. So it wants to go back to that natural state. And so we help them by using water and other corrosive environments, it actually corrodes quickly. So the problem is in these closed loops, if you don't take care of them, they actually start restricting flow through the systems there, and then you lose heat transfer efficiency on the equipment. Okay, so the potential loss of energy. Obviously, to optimize your energy dollars, you certainly want to watch your approach temperatures on your machines. It doesn't take a whole lot of film of scale or deposits to cost energy in these machines because they're so efficient, okay, right now. So, for example, if you had a 1/100th of an inch of scale, now that's about a thumbnail thickness or less of scale formation, assuming you have a 500-ton chiller operating 15 hours a day, 150 days per year, which might not be too off of what you guys do up here. Depending on the KW cost in the area, you could lose anywhere from $6,000 to $12,000 annually in electrical costs just by having a small film of deposition on the tubes. Water conservation. Obviously, this is a big topic, not only here in Seattle. I mean, the California has got a 2020 event going on where they're trying to reduce 20% of their water by the year 2020. Florida's got a big water conservation effort going on there. And since the buildings and hospitals and universities are the biggest water consumption, normally they're cooling towers next to landscaping. It certainly takes a good look at where we can go with water conservation. And one of the topics I'm going to spend a couple slides on is what we call concentration ratio or cycles of concentration. The more you can concentrate that water, because steam is leaving the tower at the top, so all the minerals stay behind. The more you can cycle that up, the less water you're going to use. And it's pretty drastic. Going from, think about water in, water out is probably the worst. I mean, it's water in, water out, okay? If you go down to 2 cycles, you drop almost 50%, well, you drop 50% water usage, okay? From there, for 3 cycles, you drop a fairly good amount, incremental amount. 4 cycles, 5, 6, 7, 8, 9. There is a diminishing return. Okay, you can see the graph coming down, and eventually it's going to go way out here. It'll never reach 0, 0, obviously 0 discharge. You just don't discharge anything. Okay, so you can see the incremental savings here is not as great, but still worth capturing. But if you're running up in here, then the savings are very drastic. Okay, so the definition of concentration ratio is basically the ion concentration in the recirculating water divided by the ion concentration of the makeup water. Okay, that determines your cycles. For example, the conductivity of city water here is about 74 micromoles. Okay, if your tower runs 740 micromoles, so you're concentrating it up, you're running basically 10 cycles. Okay, 740 divided by 74 is 10 cycles. At 10 cycles, you're running about 10% bleed rate. So in other words, all the water going to the cooling tower, about 10% is being removed through bleed. Okay? The higher you go, the smaller percentage of your bleed rate. Obviously, the lower you go, the higher percentage of your bleed rate. So what does that mean? Well, when you look at water's ability to either be scale-forming or corrosive, there's a couple models in the industry. So I'm going to use LSI for the purpose. This is basically a Langler Stability Index. It basically takes things like calcium, alkalinity, conductivity, pH, puts it in a model, and predicts whether the water is going to be scale-forming or corrosive. Okay? We can change that model. We can change, if we cycle up the cooling towers, we actually have different numbers. So as we go up in the LSI scale, we seem to get more scale-forming. As we go down the LSI scale, we get more corrosive. Most water treatment programs can handle an LSI of 2.5. Once you exceed 2.5, the chemistry itself really can't handle all the calcium alkaline in the water. You can still scale on top of it, okay? So what we use this model, so what I did is I plugged in Seattle water into this model and did some calculations on it to find out where you should be. Based on the LSI, the cooling towers can operate at 15 cycles of concentration in Seattle. Okay, 15 cycles. You're way out here on that graph, okay, which is very good. Now, you need good water treatment program to prevent scaling, because as you push it out there, you are going to see some deposition if you don't have good water treatment. So your conductivity set points on all your controllers should be around 1,000 to 1,100, unless you have varying makeup source waters. So one of your homework assignments is when you go back to your cooling tower controller, see if it's between 1,000 and 1,100. If it's not, ask your water treatment supplier why it's not there.